Who would like to offer a prayer for us? Get us started. Anyone? Go ahead. Have you already done it for us once?
I think so.
Oh, let's have someone else. We've got lots of people. So, President, thank you. Thank you. All right. So, trig substitutions. I probably mentioned this in class, but finding antiderivatives is so much harder than derivatives. Derivatives, you learn a few set of rules, you throw anything at you, you just keep applying the chain rule or the quotient rule and the product rule until you get to things that you know the derivative. Like, taking derivatives is not that hard. Antiderivatives, much harder. We create a set of techniques that we can apply and try out. There's a bit more strategy involved, trying to think through like what might be good here. It's not as straightforward. So we're learning the new technique of today, and these problems are pretty long. We're actually taking 2 days, so well, technically 3. Today, the lab tomorrow, and Friday we're all going to spend on trig substitution problems. Okay. Tomorrow we're going to be doing a couple problems in lab where you'll learn that your rear bike tire knows how to do a trig sub. So, and defensive backs also know how to do trig subs. So, why, you'll have to find that out tomorrow. Yeah. No, so there's no online homework. Wait, is it 7.4 scheduled for Friday? I thought we had 2 days on this thing. TAs? Yeah. Okay. Yeah, I think you have a break on the online homework, and we had 7.3s, I hope. Yeah, and that's Monday. Yeah, so you guys get a little break, you know, to study hard for your other classes where you have midterm. We've got a midterm coming up in like, 2 weeks or something like that. So after 7.5, so maybe it's a week and a half. All right. So the strategy with trig sub is if we have things like 1 minus x squared plus 1, x squared minus 1, if we have things of these forms, then there are these trig identities that we might be able to use to make things simpler, because we have trig identities of these forms that simplify to a perfect square. So especially if we're taking square roots. But even if we're not taking square roots, these forms here, we might be able to go from a sum to, or 2 terms added or subtracted, to just one sum. So that might be able to help us. So what's the one thing that everyone remembers from trig? This, besides SOHCAHTOA. And no one remembers this. So you don't have to remember the second one. All you have to do is remember the first one, and then you divide everything by cosine squared. So it's a nice trick. You divide everything up here by cosine squared, you get a 1, you get a tangent squared, and you get a secant squared. So, and if you divide everything by sine squared in that first one, you get the other one with cotangents and cosecants. So, so that's what I have to do. I don't have to do that. After you teach this enough, you remember it. But okay, so what do we use? Well, if I have a something squared plus 1, then I'm going to have x equals a tangent. Okay? Or if it's x, if it's not 1, we have to change it a little bit. If it's a 1 minus x squared, then x is going to be a sine or a cosine. You can choose. And if you change this around, you get a tangent squared. X equals secant squared x minus 1. And so if I have a something squared minus 1, these could be actually be any constants here. So then you use x equals secant, not secant squared. Okay? So, yep. Why does it work? Because you end up with equations with the same form. So if you solve for cosine, oh, these should be theta. That's my bad. Yeah, so you can do x equals sine or x equals cosine of theta. Either one, because each of them is the one minus the other one squared. It fits the same form of what we have here. So 1 minus x squared, or a constant minus x squared. I think most people like to do sine, because then you don't end up with the minus sign when you take the derivative. Well, if you do x equals cosine, you end up with a minus sign. You've got that there. So I think most people do sine. One less negative sign to mess around with. So, all right. So if we go back to this, has everyone had a chance to chime in? Okay. So what form are we talking about here? We've got an change. So this form that we care about here in the denominator, we're going to make that a perfect square. So we're going to it's the form of x squared plus something. So what form is that? We've got an x squared plus something. We're going to want a tangent. If that something is 1, then it's just x equals tangent. But this something is not 1. So we know it's either C or A. Are we going to pick 3 or the square root of 3? Square root of 3. So why is that? So it'll simplify nice, so we can actually have a tangent squared plus 1. That's what we need to replace it with a secant squared. Tangent squared plus 2, tangent squared plus 3 doesn't help us. We need to have a tangent squared plus 1. So if we replace that with, if we replace x squared with, if we do this substitution and replace x, then you get the square root of 3. You get the square root of 3 tangent of x. No, we're doing theta. Sorry. Squared plus 3 square root okay, you end up with this form, and the reason it helps us in the bottom, I haven't yet multiplied through by dx, right? So we need to figure out what dx equals. We're not going to do that right now, but you have to take the derivative. That's probably the number one thing that students make mistakes on with these problems, is they'll do the substitution and they'll forget to calculate what their dx is and multiply through with their dx. So probably number one mistake. So I want to just focus on how this helps us here and where this square root of 3 comes from. So once we square these, you get 3 tangent squared of theta over the square root of 3 tangent squared of theta plus 3. And looking at the denominator, I can factor out that square root of 3 and make it 3 tangent squared plus 1. And now I can actually replace that with secant squared. So I get a perfect square, and that denominator can simplify to just the square root of 3 times secant of theta. And maybe I can do something with those trig functions. if you had picked 3, if we had picked this one, 3 tangent of theta, we're going to be in trouble, because then you're going to square this. You're going to square the 3 here. Pick another color. If this was just 3, you would end up with a 9 here, and then you can't pull out. You can't pull out a 3, or if you do, you still have a 3 there. 3 tangent squared plus 1. 3 tangent squared plus 1. What does that equal? Not a perfect square. So you've got to pick that constant carefully so that you end up with the perfect square plus 1. So the book teaches it as finding the square root. You take the square root of that. That's what it should be. That should be your constant. Okay, question so far? All right. I'm going to kill the lights for a second. And hopefully this will work. Okay. Anyone know what curve the light is making on there? A parabola? I hear parabola? A hyperbola? Part of an ellipse? So this it's going to be a conic section. The light coming out of here is going to make a cone as it comes out. Depending on how you cut the cone, you get the different shapes. And so if you cut it straight across this way, you get a circle. You cut it off at an angle where you don't get the top of the cone, you get an ellipse. Okay? If you cut it off at just right, you end up with a parabola. But if you cut it off, if you've got your cone heading up this way and you come straight down off the center, you end up with a hyperbola. Okay? So, I looked at the light and blinded. Let's see. I'll hold the lid up. So I'm going to pull this up. I'm going to put it about right there. Okay, that was a pretty pathetic marker, but and you guys can't see it anyway because the light's off. So this is a hyperbola. Let's hear it for Emily's phone. Thank you, Emily, for letting me know. I left mine in my office. Okay. Okay. So the center of our hyperbola would be right here. I tried to make it so this is about 1 foot, and this is about 1 foot. And so I'll draw this up on here. And I tried to make it so that the equation would be y squared minus x squared equals 1. So there would be our axis. Okay, I'm going to draw this. Okay, so let me draw what I did up here. Your job is to find out the area of that shape up to the top of the board. Okay, so our board looks like this, and the light went something like this. We said this is about 1 foot. The center here is about 1 foot. So this is going to be y equals 1 here. This will be y equals 2. And the equation was y squared minus x squared equals 1. Okay? So, at your seat, see if you can set up and then solve what the area is for this region. Okay? Go for it. You can use your neighbors, TAs, whatever. So there's a couple ways to go about this, just to make sure we're on the same page. Let's set this up together, okay? So, because you can choose to slice it in terms of x, or you can choose to slice it in terms of y, okay? So you can think about finding areas with slices like this, or areas with slices like this. We're going to do horizontal slices, okay? So if this is y equals 1, this is y equals 2. We're going to slice horizontally like this, okay? So you can do it the other way too, I think. I haven't worked it out that way, so I'm a little worried if we try that way, and I haven't worked it out yet. So let's do it this way. So our integrals are going to be from y equals something to y equals something, and we have to solve here. We're going to solve for x or y. Do we want y? We want this dy? So we want to solve for x. We want our outputs to be x distances. Okay, we want our inputs to be y's. We're going to put in y coordinates. So if you solve for x, then you get a minus x squared equals 1 minus y squared, and then you get x squared equals y squared minus 1. So x equals the square root of y squared minus 1. Right, so I multiplied both sides here. I multiplied by a minus 1. So, and I just switched those. Okay, so then you have square root of y squared minus 1, and the y will go from 1 to 2. Okay, so there we set it up together, make sure we're all on the same page. So let's work it from there. We have to multiply by 2 on this too, because that will just get us this half. So we have to multiply by 2. If you want to try it the other way, you're certainly welcome to. But we're going to work through it this way. Okay, so you guys just keep working on this. I'll start writing down my work up here. Okay, so when you get stuck, you can see what I'm doing. All right. So I got to this point. I did my trig substitution with y equals secant theta. So got that right here. And I didn't forget to multiply through with my dy. An integral adds up products. Products of a function value times a small change. We need to figure out what that here this represents a small change in y. We need to figure out what that small change of y is in terms of theta. So we need to multiply through by both of those, and you get tangent squared secant, or yeah, tangent squared theta, secant of theta. Now you know why we did 7.2 before we did 7.3. Because every time you do one of these trig subs, you're going to end up with a trigonometric integral with a bunch of trig functions in there. So, and then we're using our tools from the last section. There's a couple different ways to approach this. I don't know if anyone is super slick. You can do parts, and you think about it as tangent times a secant times a tangent, and then you can make this tangent times a secant. You can think about that as a as your dv. It's supposed to be a v, and tangent of theta as your u. So, and you can do that. Yes. Oh, so why do you drop the bounds? Because these bounds are in terms of y, and these are thetas. So if I write 1 and 2 here, I'm lying. Okay, this expression is not the same as the upper expression. So drop the bounds until you get it back into x's, or you can change your bounds, right? On a definite integral, you can come back up to this equation and figure out what your bounds are in terms of theta. You can put those bounds in there if it's a definite integral. So, yes. Yeah, you will lose points if you keep your bounds on there, even if you write y equals. So, okay. All right. There's another way. Might be a little bit simpler than parts. You still end up having to do the same bad integral. You could replace tangent squared with secant squared theta minus 1. And then you end up having to find secant cubed theta d theta minus secant of theta d theta. And the second one, secant of theta, that's the one that they encourage you to memorize. There's not a great way to derive that. It is the natural log of secant of theta plus tangent of theta. And Secant cubed, they actually they do that in the book. You do it by parts. You do it by parts, and then you also run the cycle. So if you do this one by parts here, if you do this one by parts, then you think of it as a secant squared theta, secant theta, and which part do you want to find the derivative of? Which do you want to find the antiderivative of? Yeah, the antiderivative secant we already saw. It looks like that. That's not nice. That's ugly. Okay, but the antiderivative secant squared is just tangent, so that we can handle. And derivative secant is secant tangent. Tangent. So you can do it by parts. We're not going to take time to do that right now. It's in the book. It's one of the examples they do. Secant cubed surprisingly comes up 3 or 4 times this semester, and so you might want to just memorize it. It's actually not hard to memorize because it is the it's the average of the antiderivative and the derivative of secant. So the antiderivative is the natural log of secant of theta plus tangent of theta, and the derivative is secant of theta tangent of theta, but the whole thing, it's the average of those, so you have to divide by 2. So it's not too bad. But then we still have minus the natural log of secant of theta plus tangent of theta. And here we have a negative, that natural log of that. Here we have half of a natural log of that. So when you combine those, we're going to have a negative 1/2. So we could rewrite that whole thing as the secant theta. Yeah. Oh, yes. Yeah, so we could do it. We could multiply through by the 2 right now too. So we have these 2's here. Okay. So we could do that now. So then that you get the 1/2 there, but then now we have a minus 2 natural log there. So we have minus 2 natural logs. We have the 1 natural log, so that's going to end up with a minus natural log. Secant theta plus tangent theta. And if we're not done yet, we have bounds, right? This is a definite integral, but we have found the antiderivative in terms of theta. So now what we need to do is get them back in terms of x's, or you'd need to convert your bounds to thetas, which in this case, it's hard either way. Question there, then question here. So the antiderivative of secant cubed is right here. This part came from the antiderivative of just secant. Yeah. This is one of the disadvantages of projecting a screen, is I can only show so much at a time, so it's easy to lose. If you want, by the way, if you want to keep track of things, you can pull out your phone and take pictures if you want to go back and refer to them during the class. I've looked into technology, like, if I could do this on a Google Doc, then I could just share it with all of you, and you guys could have real-time access, and so you could go back and see what I did. They have a J... Now, let's talk about math. But you don't have to... It canceled with the 1/2 here, and so it's not the 2 secant tangent, because this 1/2 was multiplied by that, and the 2 would be multiplied. Yep. And this 2 here, we had a minus 2 of these, and we had 1 of those, and so you end up with just a minus 1 of those. All right, I'm gonna convert back to x's because that's what we're gonna do most of the time. Instead of changing bounds, they turn out to be pretty much. You have to draw a triangle in this case either way. So I do mean y's because I'm doing it in terms of y. Thanks. So I guess you don't have to do it if you change your bounds. You get something you can actually just punch into a calculator. But it includes like tangent of inverse secant of 2. So, okay. So our original. So how do we do this? We go back to our original substitution. Y equals secant of theta. And I build a triangle. If I think about theta as an angle of a triangle, secant is a ratio of 2 sides. I can think about y as y over 1. Okay? Which you may have noticed that e down here. What does e equal? This expression? It's just 3. This is just what a mathematician sees when he looks at 3. The e cancels out with the natural log. The x divides over the x. 3 to the 1 power. X to the 0, y to the 0 is either 0 or just 1. Add 1 and subtract 1. You square and you square. You got all those extra things hanging around there you can use if you want to. That's the way mathematicians do it. That's kind of what we did here. We're thinking about the y over 1. Y is y over 1. So secant is adjacent over hypotenuse. Sorry. Cosine is adjacent over hypotenuse. Secant is 1 over cosine. So secant is hypotenuse over adjacent. So y1 square root of y squared minus 1 squared. And you better end up with the similar expression that you started with in your original problem. So we had a y squared minus 1. Better have a y squared minus 1 down here. Now, yes? It's all the time. So, yeah. Well, no, like if you end up with something that isn't what you were trying to take care of at the very beginning, then you've probably made a mistake somewhere. So, yeah. Then you must have made a mistake somewhere. At least for all the problems we will give you in this class, it'll be the same. All right. See if you can use this triangle now to find out, to write this expression in terms of y. Okay? Can you write that, use that triangle, can you write that expression in terms of y? Yep, that's right. Nice. Okay, I'm going to start to do this. Do you want me to talk through it while I do it? Snap if you want me to talk through it while I do it. Okay. All right. So secant of theta. I don't have to go to the triangle for secant of theta because I already have that secant of theta equals y in this equation. So I can just replace that with y. Tangent of theta in this triangle, I look at theta. Tangent is opposite over adjacent. So I need that divided by 1. So that part's going to be this minus the natural log of, and I already know what secant is, it's y, and I already know what tangent is. It's the square root of y squared minus 1. And then I can now I can plug my bounds in from there. Y equals 1 to y equals 2. Has anyone punched this out on their calculator? Two squared. Yeah, do you get can you get a decimal approximation for us? It should be between 1 and 2. So, because on our picture, This is 2 feet wide, and it's 1 feet high. So I'm hoping. Dang! I thought this would be 2 feet wide. 2.147. Okay, my intuition might be off then. So, okay, thanks. Still, I was thinking this would be 1 foot, but maybe it's more than 1 foot. Oh yeah, it is longer. Didn't you have to solve for this length here, from here over to here? It's square root of what? 3. Oh, so it's longer than 1 foot. So that's the square root of 3. Great. Okay. Let's talk about another area problem. This is the top part. Oops. There's the lower part. Okay. So some pieces of the circle are pretty easy to calculate, but some areas are not so easy. So what we want to calculate is this area from 0 over to A inside that circle. So this is a unit circle. The radius is 1. So it's x squared plus y squared equals 1. So see if you can set up and start to solve this, solve for that area. Alright, so here's my work so far. I went back to my equation, solved for y, because I planned on integrating with respect to x. So I'm slicing this way, so I need x as inputs. So y equals plus or minus the square root of 1 minus x squared. Positive 1 is my upper one. So my bounds are 0 to a, square root of 1 minus x squared dx. I picked sine, because I know 1 minus sine squared would be cosine squared. I found my dx here, and I multiplied that through. All of that is my dx. So I ended up with this part simplifying to just cosine of theta, and ended up having to find the antiderivative of cosine squared, which you do with the half angle formula. I encourage you guys to memorize it because it just comes up tons of times. Saves a little time. So this, if I memorized it correctly, is the antiderivative. So if you don't have it memorized, the half angle formula is 1/2 plus cosine of 2 theta all over 2. And so you can see where that piece comes from, the theta over 2, and then you do a u sub and you get this piece. Okay, yes? Yeah, so you can go either way here. I'm going to get it back to x's again, just so we can practice doing that. You can go up here and you get x equals sine of theta. You can solve for theta. It's really nice on this piece with the theta over 2, because then that means you're just going to end up with, we have to do this anyway, theta equals inverse sine of x. So put this over here. So inverse sine of x over 2 plus, now what are we going to do with this piece? I can't read sine of 2 theta right off of a triangle, so I have to use a trig sub here. So I'm going to replace that part with 2 sine of theta cosine of theta, and sine of theta, I already have what that is from my equation, so that part's just going to be x. And cosine of theta, to figure that out, I'm going to draw my triangle. So sine of theta is x. Sine is opposite over hypotenuse, so x over 1. And so this will be the square root of 1 minus x squared. So I'm getting kind of small there. Let me draw that again. 1 minus x squared. So what's cosine? Cosine is adjacent over hypotenuse, so it's going to be the square root of 1 minus x squared. Okay? Yes. Yeah, this is arcsine. That's right. That's right. So that part is just cosine. So so this piece became 2 sine of theta cosine of theta over 4. And so that those divided out, and I still end up with that 2 there. Okay? And then I haven't, sorry? Yeah, so this is our original substitution here. That's how you build your triangle. So, is that what you meant, Brian? Okay, but we haven't plugged in bounds, so we're going 0 to a, x equals 0 to x equals a. So inverse sine of a over 2 plus a times the square root of 1 minus a squared over 2 minus inverse sine of 0 is 0, and once I plug in 0 into that x, that becomes 0, so I just end up with this much. Now, I don't have time to do this really well, but if you chopped up this area that we just found in terms of a triangle and a circle. This is I'm not an area and a triangle and a section of a circle. So this is a horrible square root sign. This is the square root of 1 minus a squared. So this part, what's the area of that triangle? A times the square root of 1 minus a squared over 2. It's right there. And how about this piece? That is the inverse sine of a over 2. Inverse sine of a is an angle, and what angle is it? It's this angle. You can see it actually from this angle better, but we don't have time to go walk through the whole thing. But it's this angle in terms of radians. The angle of the whole circle is pi r squared, which is just going to be pi times 1 squared. But how much of that circle do we have? Well, out of 2 pi radians, we have inverse sine of a, and the pi's divide out. That's 1. We just end up with that piece. So, pretty amazing. All right, have a great day.
Before you close down, I just had a question.
Yeah.
Is it okay if I was just looking at when you were solving for theta, and it was when sine of 2 theta, and you had to switch over right there.
Hold on, let me stop the recording.